Okay, so this is so sick. But that's the Pareto, but that's not the Pareto plot. Oh, wait, SF. Oh, this is so sick. This is camera boom. All right, so what you're looking at was the percentage. Safe fraction front, 75%. Gear ratio. Yeah, okay, so the base motor, the elbow motor, and the wrist motor. Total motor mass. Safe fraction. Safe fraction front. What does that mean? Safe fraction front. But so basically, we have a table of stepper motors, and they have different holding torques and weights. Why does it say weight, actually? That's weird. Weight? That doesn't make any sense. But the amazing thing is, like, basically, the whole point is gears. Okay, so the whole point is, like, if we look at the plot here, um, even our best um, thing, we're using near 20 kilograms of motors to move a payload of like 1.5 kilograms. And we still don't even get all of the area. Because how many 0.7 meter in feet? That's too small. We might need to change the links, but that's fine. Dude, vibe coding, it just allows you to work like it just allows you to move with your mind, bro. It's the bicycle for the mind. For real. Like, I would never be able to do this, dude. I mean, this is like 1,000 lines of code. Okay, so wait, how do I want to present this? Um, So I think I probably want to wait, let's look at this. Why do Oh, here we go. I wonder how much this would cost. And I would wonder, actually, there's another interesting problem. Um, Wait, is that true? I thought we did. Results, coverage versus Matt, phone. Okay, let me plug in my computer and then I'll start making the presentation, I think. I do want to write it. Maybe I'll just write it on paper. No, I'll type it. I'll type it out. But maybe just to get something in my own words so that I understand what the heck is going on. Dude, this project is actually so fucking fun. This would have sucked to do without Codex, man. Pure efficiency? Because weight in grams doesn't make any sense. It's either mass in grams or weight in newtons. Wait, but I thought that it wasn't shown. Where is that plot? Yeah, it's not shown. Maybe that's old? I don't think so. It's clearly not visible. Well, let's see what if it fixes it. Test? Okay. Dude, this thing is so cool, man. I also want pseudocode. So okay, wait. So let's look at the slides outline. I think the first slide is good. What if I built this? Does it say, what does it say about a free body diagram? So motor data, but we also want not just the motor data, but we want the linear mass density thing. All right, so I want to finish this right now. So let me. um, Worked for 10 minutes. That's so fucking cool. Wednesday by 3 p.m. Um, Yeah, okay, yeah. Oh, that's clean. Damn, that looks so clean. Oh, I didn't even realize it. Yeah, okay, that's beautiful, dude. That's great. I didn't even realize that there was a negative. Whatever. This has mass too, right? So bro, oh, this is so good. I don't understand this plot. Oh, is this the mass? Oh, this is the motor mass. Yeah, so this plot basically shows what I said is that if you don't for 100%, right? So kind of the best thing definitely is to use a 3-to-1 gear ratio. That's a great plot, dude. I like that a lot. Damn, that's nuts, man. For the phone, even the phone, you need a 30 to 1. Yeah, basically a 30 to 1 gear ratio. That's pretty interesting though. Wait, kilograms, centimeters? That doesn't even make sense. Holding, bro. This thing makes me want to build it, man. This is so hype. It's actually so hype. No way. Dude, the fucking arcs are not in the right spot. But let's see in the final report, does it um when we have the motor table. Okay, it's in Newton meters. Okay, so then I don't care. As long as it's right, I don't really care. I think we're gonna have to iterate this on a little bit more. Wait, let's go to the It's getting there, dude. It's actually getting there. Let's look at the figure. Bro, it's still wrong. Dude, what? Dude, what is it not seeing, bro? It is not getting it. It's pissing me off. Oh, beautiful. Oh, beautiful. Okay, good. All right, so this looks good. What? Bro, what? What? Oh, what? The SVG path looks great. Actually, I think I'm gonna revert that. Actually, I don't care. That's fine. Good enough. All right, it looks good. This actually seems sick. Oh, it's just a bundle? Okay, wait, let me read the final report. The fact that it did this is so weird. Bro, I had no reason going this hard on this project, but I had to. I had to, man. Yeah, what's the difference between this? They you have the same mass, but one has better torque. That's weird. Why did it do a log plot? I don't really feel like that. But whatever. I mean, it's chill. I should bring in a stepper motor. I should bring in a stepper motor and some T-slot. That would be fun. How am I gonna do this in 3 minutes? I'm gonna have to cut it down. All right, I want to do it manually. Let's just do this thing. What if I built a robotic arm to hold my camera? Okay, so the first thing is um, problem. There exist many motors to use. The main trade-off is actually, I think I should start with the free body diagram. Wait, actually, let's see. Oh, we can't use SVG. What if I built a robotic arm to hold my camera? What is a camera arm? Three links, three motors. Here's a free body diagram. We have a clamp here that connects to my desk. There's a moment about this. Then we have two extra motors. So there's a motor to hold this angle, a motor to hold this angle, and a motor to hold theta 2, where this is theta 0. Then we treat each linkage with a linear mass density and some length, and that the uh, weight is applied at the center of mass, as is typical. We also assume that the motors themselves have mass, and that's going to be important right here, where we have a large variety of motors that we could pick, and we now need to find the right combination of motors to hold up the camera in all the angles that are possible. So here's a plot in log scale that we have really teeny motors that don't really have any holding torque up to these beefy ones that are like 11 kilograms or, quite large. Okay, so then we should say some additional assumptions table. Oh, I'm getting a phone call. Hey. No, let me read it. Oh. Bro, that's actually so sick that we can iterate on slides just like this. How do I fold all? There we go. Build deck? Dude, ain't no way, bro. Build deck? What the hell? Oh my god, not the presenter notes, bro. Why am I doing all this? Okay, wait, but let me do this just for the flow of what I think would be best. What if I built a robotic arm to hold my camera? What is a camera arm? It's 3 links, 3 motors. That's the free body diagram. There's a moment about each motor, and that moment basically has to be less than the holding torque of the motor. Now we also have a resultant for the clamp at the desk. Then we assume that there's a uniform linear mass density for each of these linkages and that it's the same across it. Now I modeled that off of this stuff called 10 by 10 T-slot linear aluminum extrusion. So I just looked up a figure for what that is. But here's the problem with this is what makes the problem interesting. We want to hold up my camera, which is about 1.5 kilograms. The problem is there's a ton of different stepper motors, which are motors that allow us to move to a precise angle. And the main trade-off is how much torque do I want or need, but how much mass does that motor have? Because the more torque you get, the more mass the motor has. And essentially the problem is if we put a really beefy motor, and the 3 motors I'll call the base motor, the elbow motor, and the wrist motor. And the major problem is that if I put a very heavy motor at the wrist, now all of the motors before it are going to have to hold that up, and it's going to contribute to the moment. So what we want to do is find the right trade-off. And here's just a plot that shows basically on a log scale the offerings from 2 providers, Pololu and Stepper Motor Online. Here's some additional assumptions that I made, about the lengths of the linkages, the linear mass density, and other stuff like that. But let's get into the actual. Bro, let's fucking do it. That's so sick. That is so cool. Actually, so freaking cool, man. Oh, I moved this. Let's go back. Okay. Okay, so let me see. What if I built a robotic arm to hold my camera? The question is, can real stepper motors statically hold my 1.5 kilogram camera? Now, what am I solving? Given a payload and some geometry for how 3 link. Actually, I don't even like this. Let me see if I can just. I think I'm just gonna do it myself. Maybe this is good. Maybe I can salvage this. It's just kind of too um yeah, a little more coffee. Muted? Oh no, I just okay. Brother, hey, baby, me up. I'm up there. Dead up, dead up. Dead up, dead up. Okay, what if I built a robotic arm to hold my camera? Let's add some fluff to this. June 17? What if I built a robotic arm to hold my camera? What is a camera arm? 3 links, 3 motors, 1 camera. Okay, so because it manually did this, but I don't like that. Can you edit the types report so that I easily have? Okay, so wait, what else do I need here? So known values. Okay, so this is gonna be the most. This is gonna be the thing that I actually have to like grind out. Okay, so then example solve. So back to this free body diagram. Let we will pick motor choice, beta choice, and then we solve it. Okay, and what we find is um, for a fail point, and then we solve that. Do these slides actually do a solve?
There's no solve. I know what she wants to see. Um, or do we have them? Ta- report table exports. Let's see. Actually, if I just go to the report, where's the fucking thing? What the hell? Um, actually, let's just get some progress done because I don't know what I'm doing, man. All right, so let's copy. Let's just get a stepper motor. What? Bro, it's lagging. It's lagging. Okay, so we got a stepper motor. And then let's get some PNG. I need a PNG. Just do this. I mean, what's the big deal? Where's the 80/20? Actually, I don't want to commit to that. Is it Polulu? Yeah. I'm gonna fix that one. So we go here. We go to motorcandidates.png, copy it, paste it, scale it. What if I built a robotic arm to hold my camera? What is a camera arm? 3 links, 3 motors, and a camera. The components of the arm are these things called stepper motors and T-slot aluminum extrusion. Now, I found the linear mass density, and I assumed all linkages have the same linear mass density from this website, and it was shown in the next table here. Oh, wait. Shown in this table. Let's put the assumptions actually up here. Okay. All right, what if I built a robotic arm to hold my camera? Robot arm, camera. There's 3 linkages and 3 motors that are used, plus the load, which is this camera that I have, which is about 1.5 kilograms. Now, the main components of the arm are going to be 3 what are called stepper motors, and then 3 linkages, which are made of this T-slot aluminum extrusion that I found the linear mass density of by looking it up from this website. Here's some additional assumptions. I made the links quarter meter, and a fifth of a meter. Then here's the linear mass density. That's just what we're going to be using. So then you can quickly calculate what the link masses are going to be. Now, as we'll see going forward, the camera mass is actually quite heavy for direct drive of the system, which means no gearing. So I also included the mass of my phone as an alternative to see if we could at least control my phone camera. Now, gravity, and then here is something that I'll get into is the safety factor. Basically, each one of the motors has a holding torque, but we may want to artificially increase or decrease that torque so that we know it can really hold it. And then gearing, maybe I'll get into gearing if I have time. This is a free body diagram to better explain it. So the first 3 of these nodes are motors. And we see that that there's only one pin in our free body diagram, which is basically the motor that is clamped to the table. All the other ones are in free space, not tied down to anything. And then, each linkage has its own center of mass where there's a weight applied, so a downward force. And then similarly, each, the load and then the two other motors also have it, downward weight. So what's the problem? There's a ton of different motors, and you pay for more torque in mass. And the problem is if you put something really heavy, like the camera, at the end of your robot arm, you have to pay for that with all the previous motors. So this is a plot of a log plot of the motor mass and then the holding torque. And you can see that there's a wide variety of stepper motors that you can purchase. So here is an example of the angles and the motor choices that we pick. And we'll just walk through the basic math of what the resultant forces are and the resultant moments are for each of the motors. And then we'll compare that to the holding torques. And we see that it fails. And this makes sense because, as I've seen before in my own projects, direct drive is pretty terrible most of the time. I built this Nerf shooter a long time ago, and I tried to just direct drive the mount, and it didn't work, and I had to switch to everything being highly geared, which the main cost of gearing is slowing everything down. So the advantage that we may want is if we wanted to move our camera quickly, then we could direct drive potentially. Dude, doing this in 3 minutes is going to be impossible. Like, what if I just time myself right now? All right, let me try this. What if I built a robotic arm to hold my camera? So the camera arm will consist of 3 linkages connected by 3 motors and hold a payload of a camera at the end. Now the components of the arm are going to be these things called stepper motors, and the linkages will be made of this T-slot aluminum extrusion. Now the stepper motor data that you'll see later comes from these 2 providers, Pololu and Stepper Online, and then the linear mass density of this, what I had was 10 millimeter by 10 millimeter aluminum extrusion from this website, 8020.net. Now, these are the assumptions. I set the link lengths to this, quarter meter, and 0.2 meters, respectively. Then the linear mass density ended up being about 3/4 of a kilogram per meter by this 1010 aluminum T-slot profile. Then I actually included 2 different camera payload masses, one for the actual camera, which was about 1.5 kilograms, and the other, which was about 250 grams, which was my phone. Now, I also include some safety factor and other stuff like that, that if I have time, I can get into. I'm already a minute down. This is the free body diagram. We have 3 linkages, and then the first 3 nodes here are motors, and then the last node is a camera. We see that there's only one pin joint here with the resultant RX and RY force. And that's because this first joint is considered clamped to the table, but there's still a motor that holds this angle theta 0. And similarly, the second motor holds theta 1, and then theta 2 is the third motor. And we call these the base, elbow, and wrist motors. And then, of course, the linkages themselves have mass, and we went over that, and we assume that their weight is applied at their center of mass. Okay, so what's the problem? There's a ton of different types of motors, and we want to find which combination of motors we actually can use. And the interesting thing is that you pay for having more torque with mass. And so if you put a really heavy motor at the end of your arm, you now have to pay for that each linkage in each motor before that. So here's a plot of a log plot of all the motors. Here's an example solved. So we choose theta 1 is 20 degrees, theta 2 is 30 degrees, and theta 4 is 10 degrees. And we can walk through finding the resultant RX and RY. RY is 0 because there's no Y forces. It's all gravity. RX is basically the sum of all the linkages, and mass, and weight, and all the motor weights. And we arrive at RX. And then finally, the most important is the torques for each of the Okay, wow, 3 minutes is brutal, dude. That was 3 minutes. Bruh, 3 minutes, it actually fucked up. Damn. Um, Control Shift what, comma? Oh, nice. Okay.
What are the dynamics if the arm is accelerating? What changes about the analysis?
Um, Where's the phone one? This is surprising, man. All right, so let's get through this thing. But dude, I actually have to do this part. This is like the important part. Damn, that's a big crow. Wait, I want the pseudocode too. Where's the pseudocode?
Freaky ass. Freaky ass. Freaky ass. Boy, freaky ass. Boy, freaky ass.
Damn, son, where'd you find this? Okay. Where are y'all at? All right, let's reset this slideshow. Start. What if I built a robotic arm to hold my camera? What is a camera arm? It's going to be composed of 3 links and 3 motors, and it's going to hold a payload of a camera at the end. You can see this is 1.5 kilograms. Okay, what are the components? It is going to be made of stepper motors at the base, the elbow, and the wrist. And then the linkages will be made of this aluminum extrusion. Here's some assumptions of the link lengths, the linear mass density, which was found online. I measured my camera, and I also measured my phone, because it turns out that actually building a robotic arm with the motors to hold 1.5 kilograms is pretty challenging. So this is a free body diagram of kind of what it looks like. For the current problem, it doesn't matter. We can assume that it's in a plane and that there's not a yaw or pitch or whatever angle. So we have basically a clamp that clamps to the desk, and so that's going to be a pin joint with 2 forces going this way. Then we're also going to have a moment here, and that is basically the moment that this torque, the base motor, has to be able to withstand in order to not fall. And so similarly for these 2 motors, we'll also need to be able to withstand whatever the torque or moment is for the rest of the system. And then finally here we have the payload, and then the linkages also have mass, and we apply that at the center of mass. Now the problem is that there's a ton of different types of motors that people offer, and you can get more torque, but you pay for it with more mass. And so this is a plot that shows a log scale of what kind of motors you can buy. So we're going to take an example of our free body diagram and just do a solve here. But that's a little bit boring, because what we want to know is, for all the possible choices of motors and angles, and it turns out that, of course, the worst case is when you're fully extended to the side, because that's when the torque is the maximum. But what we want to know is, for a given motor choice, what percentage of theta space can we actually withstand? And so, and one thing for this solve, of course, direct drive failed. I built this thing to shoot Nerf balls a long time ago, and I didn't understand anything about statics, and I kept getting frustrated when direct drive failed, and so I had to gear it with actually worm drives, which aren't back drivable. So whatever. So my additional questions though are, what happens when we incorporate dynamics? What happens when acceleration actually changes the forces on the system? And what do we have to take into account then about the analysis? So anyways, I actually did a bunch of simulations, because I used to be a software engineer, of this is some high level code. This isn't the actual code, it's messier. But basically, for every theta combination and for every motor combination, what is the best we can do for the percentage of what I consider theta space or the workspace can we actually withstand? And so for the camera case, direct drive, it turns out even if you use more than 25 kilograms of motors, only about 18% of the workspace you can actually hold. And so that's really terrible. And so that just shows just how bad direct drive is. This is another plot that just shows that theta space more clearly. It shows in terms of the camera X position and the camera Y position, what can we hold for a given motor combination. So you can see the motor combination up here. We also include a safety factor, because presumably we want to have a safety factor. So that's basically how much additional torque do you need. So anyways, if we reduce the safety factor to 1, we can actually find a combination of motors at about 17.5, 18 kilograms that gets us to about 75% of the workspace. But that's still really terrible. You want 100%. So then I switched to my phone, and it turns out that there is a combination that gets pretty good with a safety factor of 2. And we finally, if we can take a safety factor of 1, we finally get a combination of about 12 kilograms of motors that gets us to our desired result of 100% safety. And obviously this is with a safety factor of 1. So this is basically just goes to show gearing is so important. Damn, that was 4 minutes. I really don't know how I'm gonna do this. How are you supposed to do this in 3 minutes? Um. That's actually so fucking good, man. Wait, what? You got the wrong thing. You got the wrong thing. It got the wrong thing. Oh no, it got the wrong thing. Okay, wait, let's put this in the center. What am I doing, bro? Wait, why is... Oh, yeah. think it's fine, right? I wish the DPI was higher. I don't know why it's so low. Hmm. Nice. Okay, good. So wait. That one's fine. Okay, this one needs to be fixed. The motor mass versus torque. What? Why didn't it size it right? I don't get it, man. No, that looks better. That looks better for sure. This is the main one. Not phone, full camera, not geared. Full camera. Coverage versus no, bro. This is the one. Bro, what is going on with this copy business? They really should have done 600, man. That one looks especially bad. But let's so wait, which one? I fixed this one. I need to fix this one. So this is the coverage. This is the workspace plot. Direct dry safety factor 2. I don't know what the deal is. I don't know what the deal is. I don't know what the deal is. Okay, safety factor 1. So that's going to be this. I feel like it was doing that thing before. Okay, phone. Yeah, I think it's good. All right, I gotta get to class. Should I do it one more time? Should I do it one more time? Should I do it one more time? Oh wait, I have to turn off my. Yeah. Okay. All right. Slideshow. 3, 2, 1. What if I built a camera, a robotic? Oh my god. I'm too hyper. What if I built a robotic arm to hold my camera? The camera arm will be made up of 3 links and 3 motors and a payload camera. This is a picture of my actual camera. This is not a picture of my actual robot. Now the components of the robotic arm will be made of stepper motors, and the linkages will be made of this T-slot aluminum extrusion because it was easy to find its linear mass density. Now, here's some assumptions about the link lengths, the linear mass density, the actual link masses, the camera mass, and actually my phone camera mass, because it turns out that the actual camera is quite heavy. This is a free body diagram, so we see that we have a clamp pin joint here with an RX and an RY for where the arm actually attaches to. Then we have linkages where their weight is applied at the center of mass. Then we also have a moment about each joint, because this is basically the moment that the motor will actually have to hold in order to not fall over. And then finally, the last node is just the payload weight. And so, and the important thing to note here is that each of these motors has its own weight. And that's an important point, because if we want to find the right combination of motors, then we need to make this torque mass trade-off. And there's a ton of different types of motors that we can pick from. So we need to actually go through all of our combinations and figure out what the best kind is. Because presumably we don't want a really weak motor at the base and a really heavy motor at the end. Now, this is a sample solve. So this is the most simple, but also the hardest case, where theta is 0 for all angles, because it's fully extended. So the torque is actually the most. And we also, in this example solve, just used the standard motor type of NEMA 17. So it has a given mass and a given rated holding torque. We also include a safety factor because presumably if someone bumped it, we wouldn't want the whole thing to collapse down. So this is the free body diagram of that system. It doesn't have the RX and RY, and it doesn't have the moment arcs, but we can see from this, it's the same. So here's the calculations. Basically what we do is we calculate the resultant forces just by the weight. The RX is going to be 0 because there's no horizontal forces on the system. It's all just weights. And so we can find that basically the clamp needs to supply an upward force of about 26 newtons. But the moment balance is the more important part. So the first thing we do is we calculate from the end and work backwards to the base. So starting at the wrist, we find that the required torque is going to be about 3 newtons. Then for the elbow, it's about 8 newtons. And finally for the base, it's about 15 newtons. And if we include the safety factor where the allowed torque that we're able to support is the rated holding torque divided by the safety factor, then we arrive at our actual holding torque that we allow. And we find that this fails for all 3 motors. So we need way bigger motors. And I actually brought a NEMA 17, and I also brought some linear extrusion. I thought it'd be fun. This is what they look like. And I actually built this Nerf launcher a long time ago, and I learned the hard way that direct drive is pretty terrible. You kind of need gearing if you want to build something like this. But the problem with gearing is that you pay for the increased torque with reduced speed. So if you want a fast arm, you kind of want to find this Pareto frontier of, okay, how fast can I go, and still hold the torque? And so I have some plots at the end that I can really quickly jump through. The additional questions, the things that I really want to look at in the future are the dynamics of the system. If the system is undergoing acceleration forces, how does that change the assumptions and the analysis? Because this is all statics, which is this class, but how do we go further to make sure that this arm will actually be safe in holding my camera and not destroy it? I want to show some of these. So I wrote this code to basically sample the possible angles that it could be at and all of the possible motors and try to find that Pareto frontier. This is just some pseudocode. I don't expect anyone to read it. And the important thing, though, is that testing all the motor combinations, even with these super heavy motors, direct drive only gets us 18% of the possible phase space or the theta angle space. And so basically, direct drive is a no-go. One thing to note, though, this is with a safety factor of 2, and this is a plot of basically the angle space itself. So if we're fully horizontal, basically, there's no way that the motors can hold. And we showed that in our example calculation. Here's with the safety factor of 1 for the camera case. Here's the safety factor of 2 with the phone case. We get kind of close, but still no good. If we use a safety factor of 1 with the phone, we actually finally get a case where we have 100% of the workspace is considered safe. But that's, again, with the safety factor of 1. Where's my gear? Oh, this is the wrong plot. Wait, but I don't want the safety factor. Wait, what? Why is this the wrong plot, dude? What the freak is going on? Here we go. Finally. And this last plot shows basically if we allow for gearing and we use a uniform gear ratio at each joint, basically what is the frontier of, given the lightest motor mass that we can support, what is the best, for 100% of the workspace, what is the best mass gear ratio combination for us? And we find that you need heavy motors, but if you use a gear ratio of about 3, you can get 100% of the workspace, which means that you're only experiencing a 3x slowdown, which is pretty good. But if you wanted really light motors, you would have to use extremely high gear ratios, like a 20. And that introduces all sorts of backlash problems and stuff like that. Bro, I'm fucking goated! Oh shit, I'm so goated! Actually, it's Codex, but, don't tell. Don't tell anybody. Alright, I have to go. I actually have to go.